Now we're going to have a look at the income effects model, which in a way is super straightforward, but turns out it's actually tricky. Yeah, quite a bit trickier. So what have we got going on in this model? We've got households, firms, energy sector. And this is a proper general equilibrium model. We've got labour going to the firms or to the energy sector. And depending on the amount of labour going in there, we've got R coming out. Something like this. I can't actually, it's too small for me to read the exact notation. And then we've got products coming out of here. And there's a whole range of different products. Product 1 is, the production function is A times the minimum of Ly and alpha R. So we've got a Leontief production function, haven't we? So given a certain amount of labour coming in, we need a certain amount of resources to make each unit of the good. And if we raise overall productivity, we're raising each equally. Yeah. So when A goes up, labour productivity goes up, but resource productivity goes up equally. Yeah. So if this was it, if this was the only product, what would happen to R over time? Can't hear anybody. It's going to flatline, isn't it? You're going to send, if you've got 10 people, you send, say, 9 of them here, 1 here, gives you just enough R. Then when A is 1, you've got like 9 here, and this needs to be 9 as well, yeah? But then as A goes up, alpha's constant, you've still got 9 here, 1 here, you're still going to need 9. Alpha R is still going to need to be 9. Alpha's constant. R is also going to stay constant. So you wouldn't get this, would you? Even if WR was constant, you should get R also constant and Y going up, which means that the share of the resources is going to go down, isn't it? That's not what we observe. So this kind of seems to make sense, but doesn't do the job. But if we start introducing further goods, Y2 is A over 2 times the minimum of Ly and alpha R over 2. So what's going on here? This second good, you're going to get half as much of it for a given A and a given amount of labour. Yeah? So it's trickier to make. Furthermore, for the given amount of labour, you need reminds me of Hercules Jansson. For the given amount of labour, you need I've totally lost my thread now. For the given amount of labour, you need twice the amount of the resource as well, don't you? Okay. So, if you've got 9 workers in the sector and you need, like, if alpha is 1, so you need 9 tons of the resource to get a unit of the product, or for your inputs to be in balance. Here, if you've got 9 units of labour, you're going to need 18 tons of the resource for your inputs to be imbalanced. So this is intrinsically more resource intensive. And it's also trickier to make because even with the extra resource and the same amount of labour, you're only going to get half the number of units of the actual good. But it's fancier. Okay. If 1 was a bike, 2 is a car, and 3 is a plane, okay, the idea is these goods are fancier as you go up. And the next one, y3, is a over 4 minimum ly alpha r over 4, and so on. Okay. So that's kind of the production structure. What else do we know about this economy? So we can write this in general form, and we can say that yi is a over 2 to the, is it I minus 1, I think? Yeah, because y1, this is just 1, isn't it? Times the minimum of lyi and alpha ri over 2 to the I minus 1, I think. Yeah. Okay. We can also say, because it's Leontief, this and this have to be equal, don't they? So we've got Lyi is alpha Ri over 2 to the I minus 1. But just let me pause for a sec. Yeah. So if we then say that, look, LRI is the fraction of, or the workers out of these total workers in the extraction sector whose resource output goes to sector I, then we can say that Ri, the resource inputs to sector I, are phi A LRI. So we can scrub Ri and write phi A LRI. And then we can scrub LRI and put it under here instead. Okay, so this is the ratio of labor to resource labor in the final goods sector to labor in the extraction sector for good I. And as you can see, as A goes up, as I goes up, this ratio is going down. So that means you need more and more labor in the resource extraction sector for big I. But as A goes up, you need more labor here, right? That pushes the ratio up instead. If you imagine just sticking on the same product, productivity is going up, which means you need fewer and fewer people to get out the same amount of resource. The resource demand is staying the same, so you're shifting people out of the mines and into the final goods sector in that case. Yeah. So in a growing economy with constant demand for your resource input, but with increasing labor productivity, you're going to be shifting people out of the mines, aren't you, the whole time? Okay, I'm going to pause again. Okay, so we've got a third result here. What is this? So, if we just look at the result, so you've got two different ways. Pause again. Okay, I was a little bit thrown because I think there's a very small mistake in the notes, so I had to think for a while there. But finally, we want an expression for Ri over Li. Okay, how much of the resource or energy is getting used for a given amount of labour altogether being used for good I. To get that, we can say, look, let's add an extra LRI on the top line here. And what that is the equivalent of doing is just adding 1 to the left-hand side, isn't it? Because that's just 1 plus what we had before. So that must be equal to 1 plus what we had on the right-hand side, alpha phi A over 2 to the I minus 1. But this is just Li, isn't it? This is the total labour used for good I. So then we've got Li over Lri equals blah, blah, blah. Okay, and then we can switch that and say Lri over Li equals, and then we can switch this and say 1 over 1 plus alpha phi A over 2 to the I minus 1. Okay, but finally Lri is Ri over phi A, isn't it? So we can write, instead of this, we can write Ri over phi times A, all in brackets, yeah, keep track of things like that. And then we can bring the phi A over here and wipe this. And we have Ri over Li is phi A over that. Okay. Tricky stuff. Okay, so let's just check that this makes sense. So imagine we've got A is very big, but I is small. So we're highly productive, but we're just making bikes for the low energy stuff. Then, what can we say about this, approximately, when A is big, but I is small? So this is small and this is big, which makes this huge, which means we can ignore this 1, because 1 plus something huge is pretty much the huge thing. So then we've got phi A over alpha phi A over 2 to the I minus 1. So the 2 to the I minus 1 ends up on top, and we end up with 2 to the I minus 1 over alpha, which says that R stays constant, doesn't it? For a given, if we've got a low I and a big A, and we just stick there, R is constant. So again, instead of this, we've got this. Okay. What about if A is very small and I is big? Then that would make this small and Ri over Li. Wow. Actually, I'm not sure that's really relevant. No, I don't think this case is relevant. In this case, we'd get, it's just phi A. But I don't think that's relevant, to be honest. No. I'm not sure that's particularly relevant at all, that whole exercise. Anyway, we've got this expression for R over L for the given good I. And then what we can basically do is say, look, we've got what we call lexicographic preferences, which means that the households choose the highest I they can afford, subject to some minimum level of consumption. Okay, so they need a certain number of units. And I'm trying to decide how much of this to go through. I don't think I'm going to go through the details of this. You don't I wouldn't ask you to reproduce this in the exam. Okay, not the stuff, certainly not the stuff I'm not going to go through. Okay. But what's the intuition? So let me just write down what we've got on the slide. So we're going to normalize the wage equal to A. And then GDP, if we look at it as the sum of factor payments, it's just A times L, isn't it? AL. And we've got L identical agents. And then we're assuming lexicographic preferences, so they'll buy the most expensive thing they can afford, subject to the restriction that the number of units of it must be at least C. Okay. So if they can't afford C units, then they'll shift down a level on I to a simpler product. Okay. So it's like, if you imagine like food or something, you need a certain amount of food, but you'll buy the flashiest food you can afford. Okay. And you need a car, but you'll buy the most expensive car you can afford, given the limit that you have to have one. That's the idea here. So what's going to happen as, basically it's pretty straightforward, as A doubles, the wage doubles, GDP doubles, and you add 1 to you shift up the ladder by 1 step in terms of what you can afford with your doubled income. And when A doubles, but you shift up a step, the energy use is going to stay the same, isn't it? Sorry, no, the energy use is going to double, because this bottom line stays the same, yeah? A is doubled, you've added 1 to I. So this stays the same, because adding 1 to I means multiplying that by 2. This is multiplied by 2, so this term is the same, that's the same. So you've got Ri over Li is phi A over something which has stayed the same. So A doubled, R doubled when I goes up by 1. I hope you can follow that. Okay. So what's the point of that, really? So it's kind of an archetypal case where you've kind of built a lot of math to really nail down. It might feel pointless, but it's kind of good exercise, because you're nailing down exactly what you need to assume, or you're giving an example of what exact assumptions could give you this result, driven entirely by income effects. Okay. What do you need? You need these lexicographic preferences that you always choose. You don't care about price. All you care about, you want the highest quality you can afford. And how do we define what you can afford? It's that you need a certain number of units per week or year or whatever. If you can't afford that number of units, you shift down at 1 level of quality. And if the quality levels are associated, a sort of doubling in quality is associated with a doubling in the intrinsic energy intensity of the good, that will exactly cancel out the doubling in the productivity that allowed you to shift up to that better good. So you got twice as rich, cars got twice as efficient as did planes, but the people who were previously driving cars don't carry on driving cars, they shift to planes. And therefore, their energy consumption still goes up, despite the increase in the energy efficiency of cars and planes. Okay, so that's just an example of how you can actually capture that in a model. Okay, yeah. And then, of course, the interesting thing is, like, what happens when we start doing policy. Okay, so let me just think about that. Okay, so now we're thinking about rebound. So, if you remember the production function, this alpha is kind of like energy efficiency, isn't it? When alpha goes up, you need less R for each and every one of these products. So if a regulator can like subsidize research in energy efficiency or something to push up alpha, what's going to happen? At the product level, there's absolutely zero rebound, is there? Because you've got Leontief here. So when alpha goes up, making a unit of Y1, you need, per unit, you need less R, full stop, which is not the case, for instance, with Codd-Douglas. But because there's Leontief, that is totally unambiguous. But then the question is, will raising alpha cause a bunch of people to be able to afford to shift up a level? Okay. And that is a kind of income effect, effectively. If there's an exogenous raise in energy efficiency, which brings prices down, that is as if people got more income. But to cut a long story short, as long as the energy share is pretty small, then this income effect is pretty small. So if the share of energy in costs is around 5%, if you raise energy efficiency by 10%, you will reduce overall costs by 0.5%, won't you? 1/20th of 10. Sorry, you will reduce, I'm not sure what I said there, you'll reduce overall costs by 0.5% if you raise energy efficiency by 10%. So that's a big, so the direct effect is a 10% less energy use. The indirect effect is a 0.5% income increase for people. And that 0.5%, it might mean that sort of 0.5% of people, very loosely, might shift category. But the 99.5% who don't all have 10% less energy use. So that's not really a very good explanation. The point is the income effect is going to be very small. Okay. Without doing the math properly, it's kind of hard to show that. But yeah, I think we'll leave it there. Basically, as long as the share of energy compared to the share of labor is small, like 5%, 3%, then raising energy efficiency, say by 10%, cutting it, which gives you a baseline cut in energy use by 10%, is giving you extra income by 0.5% or less. That's hardly going to affect people's energy demand through the income channel. So basically, there's hardly any rebound in this model. So it's pretty cool to try to get firms, if you can, somehow make them raise their energy efficiency. On the other hand, how much does taxing energy help? That argument goes into reverse, since the energy costs are a fairly small part of the costs of each good. Even if you put a pretty big tax on the energy, it's not going to add that much to costs, and given this preference structure, only a very small proportion of people will be tipped down into the next category. There'll be hardly any response to a tax on energy, because there's no response at the firm level in terms of, oh, energy got expensive, we will economize on it and use more labor, because we've got the onset. the only response is on the consumption side, but consumers also have very little substitutability between the goods. They basically only have this income effect. And again, because the energy share is small, the income effect of mucking around with energy costs isn't that big. So, therefore, the tax has very little effect. So there's very little rebound, which is good for boosting energy productivity. You get the effect you want. And there's very little effect of the tax for the same reason, which is bad. Whereas in the high substitutability model we did before, the opposite is the case. There's a lot of rebound. But the tax, so the raising energy efficiency doesn't do a lot, but raising a tax does. Okay, which is true. We'll talk about that in the lecture, but I think you've got a pretty good idea already.